right, so this week we are looking at 6-4 and 6-5. We're going to split 6-5 into 2 days. 6-4 will be 1 day. Again, we've already done 6-4, but because of like the snow day, we had to kind of go through it quickly, so we'll just do it again. All right. And then Thursday we'll have a review day. So in order to graph the other trig functions, first we got to remember what we did with sine and cosine. So we had two graphs, right, sine and cosine, and generally when we sketch them, we just sketch one. What do we call the thing that we sketch? One, yes, yep, one cycle of the graph or one period. Okay, which one of these is sine and which one is cosine? Yep.
Sine is the one on the left, cosine is the one on the right.
Right. This is sine, and this is at 0. And where does it end? It ends where?
Oh, with a number.
Yeah, where's the end of one cycle in radians? Yep.
Isn't it 2 pi?
2 pi, yep. And what was the middle halfway point? 1 pi. And then, well, if I want to put it on the graph, it would be right here. What's the x value of that point? Yep.
Pi over 2.
This one was pi over 2. And how about this one down there? 3 pi over 2. And on the cosine, it's the same points. 0, pi over 2, pi, 3 pi over 2, and 2 pi. I wanted to erase the one I put in the wrong spot. Now, what about the highest and the lowest? What's the highest, if you don't stretch it, the highest y value in both of these and the lowest? Yep.
1 to -1.
1, -1. Yep. Okay, so we're going to use those two graphs to figure out what the graph of tangent looks like. Anyone remember how you can write tangent as a fraction? And it's one trig function over another. Yeah.
Was it 1 over cotangent?
Yes, you can write it as it is the reciprocal of cotangent. So that is correct. Thinking of a different way. How else can we write tangent in terms of the two trig functions we just mentioned up above? Yeah?
Sine over cosine?
Right, you can write it as sine over cosine. Since we can rewrite tangent as sine over cosine, and we know a little bit about sine and cosine, that's going to help us to know a little bit about tangent. Yep.
How is tangent sine over cosine?
How? So remember when we did the unit circle? So when we did that, what was the definition of sine on the unit circle? What part of the coordinate was it? So remember on the unit circle, we have a coordinate, usually like x, y, and we said that sine was the something value.
Was it the x?
Nope.
Was it the y?
Reciprocal?
Sine was the y.
No.
Okay. How about cosine?
X.
Was the x, and what was the tangent?
Y over x?
Y over x. But what's y?
Okay, yeah.
Sine over cosine. So it's one way to explain it, going back to what we learned about the unit circle. All right, so now let's take a look at this. Okay. Looking at what I just circled in purple, we have tangent equals sine over cosine. When does a fraction come out to 0? Any fraction. Yep.
When it's divided by 0?
No, when you divide by 0, that is undefined. Can't ever divide by 0. That would be undefined.
The numerator is 0?
When the numerator is 0. Okay. So then when would tangent equal 0 in this case? When
Sine of x.
when the numerator is 0 or when sine is 0. When is sine 0? You can go look at the graph of sine. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. Every multiple of pi, sine is 0, which means tangent is 0. All right? Now, what happens at a vertical asymptote? Think about what happens as your graph approaches a vertical asymptote. One of two things can happen. Yep.
The y approaches negative infinity or infinity.
Approaches negative infinity or infinity. So there is no value. As we start to approach it, it just goes up forever or down forever. In order for that to happen, you need to divide by 0. Dividing by 0 is what causes a vertical asymptote. So when would we have vertical asymptotes in the graph of tangent? Whenever the cosine is 0. Because if the cosine is 0, that's going to cause the bottom of the fraction to be 0. If the bottom of the fraction is 0, that's undefined. Undefined means asymptote. Okay, so where is the cosine 0? Well, pi over 2, 3 pi over 2. Next one would be 5 pi over 2, 7 pi over 2. It's every odd multiple of pi over 2. Once we know where we have a vertical asymptote, we can use the calculator to check a value on each side, and then we can get our sketch. All right, so let's see if we can make a sketch. So let's start with the vertical asymptotes, where the cosine is 0. Can someone give me two values where the cosine is 0? Yep.
Pi over 2 and 3 pi over 2.
Okay, so let's put vertical asymptotes at those. Pi over 2. 3 pi over 2. And we don't have it on the graph of cosine, but where would the next one be after 3 pi over 2? The next vertical asymptote. Yeah.
5 pi.
It would be 5 pi over 2. Okay. So and I can draw as many of these as I want. There's 3 of them. Let's call this asymptote 1, asymptote 2, and asymptote 3. All right, so the next thing I want to do is let's figure out where tangent crosses the x-axis. Tangent will cross the x-axis wherever sine crosses the x-axis. Where does sine cross the x-axis? Yeah?
Pi, 2 pi.
Pi, 2 pi, anywhere else?
0.
0, yeah. 0 would be over here. I'm not going to draw that section, but I will do the one at pi, and I'll do the one at 2 pi. Okay, whatever I draw in this first section, it's going to look exactly the same in the second section. Remember, these graphs repeat. Okay, so now the next thing we want to do is test a point. Okay, so use the graphing calculator and plug in a value very close to pi over 2, and then we'll do 3 pi over 2. Let's put in our formula. You can put it in as tangent, or you can put it in as sine over cosine. Same thing. Okay, and let's go. I'm going to change to what mode should I be in based on my x-axis. I should be in radians. So degrees is not what I want. Okay, when we pick a value that's close to the asymptote, how close do we normally pick? How close do I want to be? Can you give me like a number of how close? Like within?
Within 1.
We want to go closer than within 1.
I'd say like 0.1 or just 0.5.
Much closer than that. Yep.
0.001.
Yeah, like within a thousandth. We want to go really close, like within a 0.001. Think of it like a tolerance. That's what you want to be within. So if you plug in pi over 2, if I do that and hit enter, what's going to happen? So that's going to give me an error because that's an asymptote. So don't do that. Let's go a little bit bigger than pi over 2. I don't even have to figure out what number it would be. Just do pi over 2 plus 0.001. That'll just make it a little bit bigger. And we get a y value of negative 1,000. Okay, that's rounded, but the point is it's very far down. Okay, so we are way down there. Now for 3 pi over 2, do I want to check a value a little smaller or a little bigger?
A little smaller.
Yeah, first I want to do a little smaller. I want to be on the left side. So again, just type in 3 pi over 2, 3 pi over 2, and make it a little bit smaller. Where do we expect this point's going to end up? Really far up or really far down?
Really far up.
Right, it's going to end up really far up, and it's at positive almost 1,000. So way up there. So these 3 dots all need to be connected, but you have to stay as close as you can to each asymptote, but still go through that dot in the middle. So it's going to have to look something like that. That's what it looks like. Okay. And if you copy and paste it, that's exactly what the next section looks like as well. About there. So that is the graph of tangent. And if you want to see it on the calculator, do the same thing. It's going to show more sections because it's a bigger screen than what I showed you. What I did was these 2 right here. That's the ones I showed you. Okay, any questions? All right. Now, the other thing we have to make sure we understand, and I think I explained it before, is what asymptotes belong to what cycle. Let's think of this as cycle A, and the second one is cycle B. Our asymptotes are numbered 1, 2, 3. Each cycle has to have the same number of asymptotes, and an asymptote cannot belong to more than one. So how many asymptotes would be in each cycle to fit what I just said? Yeah. Well, you either have an asymptote or you don't have it. It's kind of like sharing armrests at a movie theater. I think that was the example I used. You either only one person at a time can use it. We're not going to share armrests. So how many asymptotes can we have per cycle? So each cycle only has, each asymptote belongs to one cycle, and every cycle has the same number. Yeah? 1, yeah. It's only one asymptote per cycle. However you want to think of it, let's say asymptote 1 belongs to cycle A. That means asymptote 2 belongs to cycle B. Asymptote 3 would belong to cycle C. But it has to go that way. One asymptote per cycle. If you say 1 and 2 both belong to A, then what would you say belongs to B? You can't say 2 and 3 because you already said 2. That wouldn't work. All right, so that's tangent. What function do you get when you find the reciprocal of tangent? What's the name of that one? Yeah, that's the cotangent. What do you think the formula for cotangent would be? Yeah.
Cosine over sine.
Right, it would be cosine over sine. So, how does that compare with what we just did for tangent? What do you think is going to happen? What's that?
It'll be the opposite,
Can you be more specific? What do you mean by the opposite?
like the reciprocal. Like it'll just be flipped.
Yeah, it is. So it is going to. The formula is the reciprocal, but what's going to change in the picture more specifically? Yeah.
Oh, the asymptote from the crossing points split.
Yeah. Everything that was an asymptote is going to become where it crosses, and everywhere that it crossed is going to become the asymptote. So let me put it up side by side. So I just wrote down cotangent, and let's look at the difference. Before, pi over 2 was an asymptote. Now pi over 2 is where it crosses. Pi was where it crossed. Now pi is an asymptote. So everything switches. And the direction of the curve switches. So instead of having a positive slope, it has a negative slope. Okay, but that's what cotangent looks like. Other than that, everything's the same. You have one asymptote per cycle. The other thing we should try to figure out is how wide one cycle is. Let's see, let's look at cotangent. From here to there. That's one cycle. How wide is that?
1 pi.
Yeah, 1 pi. Because this starts at 0. This is pi. So it's pi units. Left to right, and it's exactly the same thing here. This is pi units. For sine and cosine, how far do you normally have to travel for one cycle? It's not pi units. Yep.
2 pi.
It's 2 pi units. So what that means is tangent and cotangent have a naturally shorter cycle than sine and cosine. It's half as long. Okay, so that's the picture of tangent and cotangent. We're going to have to know these asymptotes, but in a little bit I'm going to give you a table that's going to summarize all the asymptotes. Okay, so we'll have something we can look at. That's what we just said. The period of tangent and cotangent is pi. Now you can change that. You can stretch and compress it just like sine and cosine. But what I'm saying is if you don't do anything to it, naturally, it's pi. What's pi in degrees?
101.
180. Yep. So that means let's try something in degrees. I can do radians, but I'm going to do degrees. Let's take the tangent of 10. You get that number. Because the cycle is 180 degrees, what else could I take the tangent of and it would come out exactly the same? Well, where's 10 degrees in the next cycle? What would it be? Yep, 190. Yeah. So 10 degrees and 190 degrees is basically like looking at, just making this up, but let's say this point here and this point here. They have the exact same answer. They're at the same y value. They're not the same point. One's here, one's here. They're 180 degrees apart, but they give you exactly the same answer. And there's another one, it'd be like over here somewhere. That would be the answer in another 180 degrees. So if I add 180 to that again, what's 190 plus 180? 370. You can add or subtract 180 as many times as you want, and you will keep getting the same answer. It's just in different cycles. And that's what this formula is saying right here. If you find the tangent of something, or the tangent of that plus any multiple of pi, or I was using 180, same thing in degrees, it will come out exactly the same. Same with cotangent. I can find the cotangent of a value, or the cotangent of that value plus or minus any number of pi's, or plus or minus any number of 180s. And that n has to be an integer. So you could add, for example, let's say in degrees, this is 180. You could add 180 one time, or you could add 180 two times, or 180 times 4. You could add it 4 times. But you can't add 180 times like 3.2. No. You have to add a whole copy of 180, and that's it, not part of 180. So transformations. No difference in these transformations compared to any other ones we've done all year. Okay, let's start with A. What would A do? Adding, or it could be subtracting, but it's inside the argument. Yeah?
Horizontal shift.
That's a horizontal shift, also known as a phase shift. It's going to move it left or right. What does B do? Yeah.
Wait, hold on. I'm just leaving my name, sorry.
So,
So what does B do to the graph? Yeah.
Stretch.
What kind?
Horizontal.
Yep, that's a horizontal stretch. Because it's multiplication inside. How about C? What kind of transformation is that one? Yep.
vertical stretch.
It's a vertical stretch. In fact, I don't want to write it that way. Vertical stretch. This one's a period change, which you say horizontal stretch. Phase shift, that was the horizontal shift. And what about D? I don't know if I wrote it. Maybe it's under the box. Yeah.
Vertical shift.
That's your vertical shift. Yep. Remember, A and B are backwards. So if you add, that would shift it which way? Left. Subtracting would shift it right. With addition, it's not. With vertical shift, it's not. Addition is up. Subtraction is down. B. That's also backwards. So the bigger that you make B, the more compressed the graph gets. So if B was 5, you would say horizontal stretch by 1/5. What would happen if B was, let's say B was a half? What would that do to your graph? If B was a half. Yeah?
Make it 2 times longer.
Make it 2 times longer. So small numbers make it bigger. Vertical stretch, that is not backwards. If C was 4, you'd say vertical stretch by a third. If C was a third, vertical stretch by a third. What else? Oh yeah, if B or C is a negative number, what does that cause the graph to do?
Reflection.
Yep, reflection. If B is negative, it's a horizontal reflection. That's an example of a horizontal reflection. If C is negative, that's a vertical reflection. It would look more like that. That's it. I think that's everything. Okay, so we're not going to spend a ton of time. We did a lot graphing sine and cosine. We don't do many graphs by hand. Most of the graphs are going to be on the calculator. All right, so we had a formula to find the period of sine and cosine. For sine and cosine, the formula was 2 pi over b. For tangent and cotangent, it's not 2 pi over b. It's 1 pi over b. And the reason that that is pi is because of this. Because that's pi. It's pi over b. All right, so looking at the A, the B, the C, and the D, how many different transformations is that? Yeah, it could be up to 6 if you had a shift, a stretch, a reflect, a stretch, a reflect, and another shift. So you could have up to 6, where the B and the C both can cause 2 things to happen. I want to know, out of those, the A, the B, the C, and the D, out of those 4 letters, 2 of them can affect vertical asymptotes. Which 2? I want to know which 2 could change the position of a vertical asymptote. 2 of them would have no effect at all. No matter what you make these values, they wouldn't do anything. But I want to know the 2 letters that would cause things to change. Yeah?
A.
A is 1. Yeah?
B.
And B, yes. Those are that's the part that will affect vertical asymptotes. The reason C doesn't is because imagine you have a line going up and down forever and you stretch it taller. It still goes up and down forever. If you have a line that goes up and down forever and you shift it up, it still goes up and down forever. So C and D have no effect on the asymptotes. So what I want to show you is, how do you find the asymptotes if they're not in the normal spot? What if they move left or right, or stretch and shrink left or right? Well, the first step is going to be to find the original asymptotes in one cycle. So if I go back to our sketch for a second, if I was doing tangent, I would say the first asymptote that I hit that's not negative is pi over 2. That's the one I would use. The first asymptote I hit that's not negative here is 0. That's for cotangent. And to remember that tangent is the pi over 2, and the one we use over here is 0, I'm going to put them in a table like this in a minute. Tangent is the pi over 2, cotangent is 0. So we're going to remember them in a second. Okay, that's the first step. If you can't figure out where the original asymptotes were, you're not going to figure out where the new ones are. So we'll use the table that I'll give you in a minute. And then it says to set the original asymptotes equal to the argument and solve. This is the argument, what's in the red box. And the reason we set it equal to the argument is because the A and the B are the only things that can affect the asymptotes. C and D have nothing to do with asymptotes. And there's, actually, that's the last step. We just have to write the answer. When we look at the graph of tangent or cotangent, how many vertical asymptotes are there in the graph? Yeah, is infinite. So can you write every one of them? No. All you can do is describe one of them and tell me how often to look for it repeated. That's how you describe every one. In general, how often does something repeat in a trig function? Not looking for something specific, just kind of something general. Every cycle. All right. Whatever behavior you're looking for in a trig function, it's going to repeat every cycle. So, once you find one asymptote from step 2, you need to put plus the period times n. What that does is that tells me that asymptote repeats every cycle. Because there's infinitely many, and it is impossible to write them all down. So the best you can do is tell me how often to look for it repeating. If there was no change to the tangent or cotangent period, what's the kind of the default period for tangent and cotangent? Yeah, pi. Yep, it would be pi. And again, step 1, you're going to have a table that's going to help you to remember that in a little bit. Okay, I just don't want to give you the table yet because I have to explain secant and cosecant first, and I want to put those in the table with tangent and cotangent. All right, so it says find the period and graph it on the calculator and show 3 cycles, show 3 periods. Okay. So if you want to show 3 cycles on the calculator, the first thing you have to do is know how long one cycle is. If you can't figure out one cycle, you're not going to figure out 3. So what's the formula we use to find the period of tangent? Yep.
Pi divided by b.
Right. Period equals, I don't know why they use t. It's pi divided by b. And b is right there. It's the number in front of the x. Okay. So what is my b value in this case? Yeah.
Pi over 2.
What's the b value?
Pi over 2. 2.
Yeah, the b value is 2. So the period is pi over 2. Okay, so that's the first part of the question. Find the period. We're done. Pi over 2. Now graph it and show 3 cycles. Okay. Well, if one cycle is pi over 2, how long is 3 cycles?
3 pi over 2.
Triple that, 3 pi over 2. So we need to set a window where the distance between the x min and the x max is 3 pi over 2. There's lots of ways you can do that. Can someone give me a value for the x min and the x max so the difference between them is 3 pi over 2? about Nick? What do you think? If you give me an x min and an x max, so the difference is 3 pi over 2.
I don't know, honestly.
Not sure, anyone help him out? What? And again, it doesn't have to be anything. Think of like the simplest subtraction problem you could do, where the difference would be 3 pi over 2. And whatever the subtraction problem you come up with, the first thing is going to be your x max, and the second thing would be your x min. Yep.
Your x max would be 3 pi over 2.
Okay, so x max is 3 pi over 2.
And then your x min would be
0. The distance between 0 and 3 pi over 2 is 3 pi over 2. So that's one way you could set your window. How high and low does tangent go? How high?
Infinitely.
Yeah, so I don't have to worry about a y max or a y min really. Just set it high enough that you can see the curve, because you're never going to see the whole thing. So -4 to 4 is fine. And the last thing is type in your graph. Tangent 2x. Don't hit zoom and then hit 7. If you do that, you're going to mess up the window you just typed in. So leave the window just like you did. Okay. And does that look like 3 cycles of the tangent graph?
No.
No.
I don't know why.
Something's very wrong. This happens a lot. Sometimes people ask me, like on a test, it looks like a straight line. Yep, it does.
Do you have to set the thing to radians instead of degrees?
Right. I need to be in radians because that's the window I use. 0 to 3 pi over 2. So set your mode.
Wasn't there like some secret thing that you had to do besides just that?
Nope, in this one, that's pretty much it.
Hmm.
You got to set your window and change your mode. Those are the 2 things. So we had set the window, we didn't change the mode. All right, let's look at it. Now answer the question, is that 3 cycles? Yeah, it's a half cycle, whole cycle, half cycle. So technically it is 3 cycles. They're not continuous.
Can't you also count the asymptotes?
Yeah, you could count. You got 1 asymptote, 2, 3. Yep, there's 3 asymptotes there. Now, if you wanted to make them connected, you could have just shifted your window half a cycle to the right, and then you would have gotten this, and that. 1, 2, 3 connected. But you'd have to shift your window half cycle to the right to be able to see this piece. But what we have is fine. Okay, so any question on that? All right. Next one is just identifying which graph is which. One of these is 2 tangent x, one of them is 5 tangent x. So if you know what the 2 and the 5 are doing, then you would know which one is which. Anyone think they could tell me which one the one on the left is? Well, Boris, what do you think?
I think the one on the left is 5, the one on the right is 2.
How come?
I have no idea.
Okay, I'm more interested in that. Why do we think, or if you don't think the one on the left is 5, you can tell me that too. But if you do, can anybody tell me why? Yep.
Is it because of like the stretch factor? Like the larger the number, the like steeper like the angle is, and then the smaller it could be like less like this way, more like going out.
Yeah, it has to do with how much you're stretching it. If this is a tangent function, and I take that and I stretch it vertically without doing anything horizontally, watch what happens. The curve in it starts to straighten out a little bit. So the one on the left, to me, looks like the curve is a little bit straighter because it's been stretched more. And if you do the same thing, but you compress it, okay, without stretching left and right, the curve starts to get more and more pronounced. Eventually, if you squish it enough, you could almost make it look flat in the middle, but it never would really be flat. But it starts to look flatter. Okay, that's the one that's not stretched as much. Okay. So any question on identifying those two? Okay, so you'll probably see some kind of question like that on the test with matching, where you have to match maybe tangent and cotangent functions. How would you type in a cotangent if you weren't sure what it looked like and you wanted to see it? Because there's no button for cotangent. So what are you going to put in? Yeah.
Sine and cosine? Or is it?
Okay, you could put in cosine over sine. Yep, you could do that. Or there's something else you could do. Somebody mentioned earlier. Yeah.
Tan over 1? Or 1
Well,
over
tan over 1 is just tangent.
Oh, yeah.
Yeah.
So it's 1 over 10.
Right, you could do the reciprocal. That's cotangent. And if I do zoom 7, now you can see it goes down to the right. Okay, but you can't always assume just because something goes down and to the right, it's tangent. And if it goes up and to the right, I'm sorry, up and to the right is tangent, down and to the right is cotangent. Because then I could do something like this. I could throw in a reflection. So now I just took cotangent and I flipped it. So that is still cotangent, even though it's going up and to the right. But the only way you would know that is if you looked at the formula I typed in. 1 over tangent. So that's negative cotangent. So there's a reflection. But you can kind of tell it looks a little different than tangent because look for the asymptotes. Tangent would always go through the origin. This graph is not going through the origin. So I know this is not a tangent. Even though the curves look like they are, it's not going through the right spot to be a tangent. If all you did was do a reflection. Okay. Any question on that? All right. Okay, secant and cosecant. Let's look at secant. How can you write secant as a fraction? Like if you wanted to graph it on the calculator. We don't have a cosecant button on the calculator either.
Oh.
Yeah? 1 over cosine. And what about if we wanted to graph cosecant? How would we type that one in? Yep.
Down.
What is it?
Down
1 over sine. So now think about cosine again. And think about sine. Where does cosine cross the x-axis again? Oh, Luke.
Which one?
Where does cosine cross the x-axis? In radians.
Don't know. That's a good question.
Caleb?
No, pi over 2.
Pi over 2 is the first one, and
3 pi over 2.
3 pi over 2. Cosine is 0 here. Cosine is 0 here. What happens when cosine is 0 in this fraction? Yeah? We'd be dividing by 0, and what does that look like when we draw it? Okay, and what do we draw when we divide by 0? What's in the graph at that point? Yep, that is an asymptote. So at pi over 2 and 3 pi over 2, we should see asymptotes. I wrote them right here. This one is pi over 2, 3 pi over 2, 5 pi over 2, and so on. Basically every odd multiple of pi over 2. Now what we'd have to do is check, I'm not going to do this one on the calculator, but we'd have to check a value a little bit to the right, a little bit to the left, and you would see on one side it goes way up, on the other side it goes way down. This, we'll call that section A. That is one full cycle of secant, what you're seeing in that purple box. Here's a second cycle. I just have to finish that piece. And put in another asymptote. That asymptote would be, where would that one be? That one would be 7 pi over 2. Okay, I stopped listing, but that's what it would be. Okay, let's call this one section B. This is asymptote, say, asymptote 1, 2, 3, 4, and 5. I just numbered them so it's easier to talk about. Look at section A. How many asymptotes belong to that section? You've got to have the same number in every section, and each asymptote can only belong to one section. Yeah? Yeah, there are 2. Pi over 2 and 3 pi over 2, we could say both of those belong to section A. Then you would say the next 2 belong to section B, 4 and 5. But you can't say 3, 4, and 5 all belong to section B. Because then what would you say? 1, 2, and 3 all belong to A? You're using 3 twice. All right. And lastly, what's the connection between secant and cosecant? They are is there a word that describes them? Yep. Reciprocals. So we saw with tangent and cotangent, they looked pretty similar because they were reciprocals. So does this one. If you look quick, you might think it's identical. But what's different about it? It's kind of like it's actually, they're even more similar to each other than tangent and cotangent, but there still is something different. Yep.
Their asymptotes are different, like they're not the same spot.
Right, the asymptotes are all right in the middle of these other asymptotes. So 0, pi, 2 pi, 3 pi, that's where the asymptotes are. So the important thing to understand with that graph is to have a full cycle. You've got a U shape and an N shape. That makes a full cycle. A U shape by itself is half a cycle. That's not a whole cycle. All right, so let's look at cosecant. Let me draw a box around one cycle. Now I want to know what the width of that box is. I think it could tell me the width of the box. Yeah.
Pi.
Yeah. We're back to 2 pi. And it's the same for these purple blocks as well. So secant and cosecant have a cycle like sine and cosine. It is naturally 2 pi. So the formula to find the period is back to the formula you use for sine and cosine, 2 pi over b. Now I put absolute value. I don't think we ever have any where b is negative, so the absolute value probably wouldn't come into play. But remember, when you're finding a period, it's a measure of how long something is. Length is always a positive number. So there's 4 trig functions that you use this formula for. Sine, cosine, secant, and cosecant. There's only 2 that you use this formula for. Tangent, cotangent. Right, so now you get the formula for all 6. What else? Let's look at secant, the graph on the left. What are the first 2 asymptotes that are not negative? They occur at what 2 numbers?
2 and 3.
What number?
Or well, pi over 2, 3 pi over 2.
Pi over 2, 3 pi over 2. We need to remember that. We're going to put that in a table. What are the first 2 asymptotes that are not negative for cosecant, the graph on the right? Yep.
Can you ask your question again?
What are the first 2 asymptotes that you hit on the graph on the right that are not negative? Because there's ones you hit that are over in the negatives. I don't care about those. That's the second and third asymptotes. I'm looking for the first and the second. 0 and pi. Yep. Those are the first 2 that you hit that are not negative numbers. Yep. Okay, so remember that for the one on the right. So what we want to do is summarize all the asymptotes we just said. And that is a summary. On the left, tangent and cotangent have 1 asymptote per cycle. Secant and cosecant have 2. This is the first asymptote you hit in tangent. This is the first one you hit in cotangent that are non-negative. These are the first 2 that you hit for secant. These are the first 2 you hit for cosecant that are not negative. And if you're thinking, well, what about all the other ones? There's a lot of other ones besides just the ones here. We don't need to remember them. As long as you can tell me where one asymptote is, and then tell me that it repeats, you've covered everything. So this is the original, and then over here is how you're going to write the new ones. You just put plus period times n. And how do you figure out that x1? That's going to come from what I explained right here. That's this. So you're going to do this. That's how you set the original asymptote equal to the argument and solve.
What is the argument again?
The argument is the red box. So I'm gonna write this down 4 or 5 more times in the table. If you're not sure how to find this, look back at this slide. Okay, whatever that slide is, slide 6. So I'll just write that on here. That explains how to find that. And it's exactly the same for that one, and that one. This is all slide 6. Difference with secant and cosecant is you got to do it twice because there's two asymptotes. Tangent and cotangent, just once. All right, so let's see if we can describe secant, cosecant. Almost at the end, but I'm not going to rush because Thursday's a review day, so. There's only 4 slides left. We'll see. All right, let's look at secant. They want us to describe the domain, the range, the period, and the asymptote. It's pretty typical thing they usually ask us to do with a trait function. Let's start with the period. That's the one I would always start with. All right, what's the trig function they're asking us about in this problem? Mia, what's the trig function? Well, just read the question and it'll tell you basically what they want you to do. Secant, yeah. So the trig function is secant. What's the formula for the period of secant? Yeah.
Would it be 2 pi over b?
Yep, it's 2 pi over b. And what's b in this case?
Secant?
B's a number.
Oh, what is
It's the number in front of x.
1.
1, because there's no number. So period is 2 pi. There's no period change in this problem. In fact, there's no any change in this problem. It's just basic secant. Asymptotes. What are the first 2 asymptotes that we hit in the graph of secant? Yep.
Pi over 2 and 3 pi over 2.
Pi over 2 and 3 pi over 2. Now you're supposed to take and figure these out. So it says, look at slide 6. All right. It says set the original asymptote equal to the argument and solve. All right. Well, what's the argument in this problem?
Secant.
What is it?
Secant.
No, that's our function. It's not the argument. So that's showing you where to look for the argument.
Oh.
Tangent's not the argument here. The argument is that red box. So let's go back to it. All set. All right. So what's the argument here? Yeah? X. So the argument is what's being plugged into a function. So set each asymptote equal to the argument and solve. So we have x equals pi over 2. X equals 3 pi over 2. Now you have to solve each one of those to get x by itself. What do you have to do to get x by itself? Nothing. You don't have to do anything because there's no number with the x. If there was a number, then I would have to, like if it was 2x, well then I'd have a 2 here, and I'd have to divide by 2. But there's no number with x, so this step is done. Set the original asymptote equal to the argument and solve. Perfect. Now, if you leave it like that, you've only told me 2 asymptotes. I want to know all of them. So what would I put on the end of each one of them to indicate that they repeat? plus the period times n on all of them. That's how you do it. And what's the period in this problem? 2 pi. That's why I had you do this first, because you can't do this without knowing that. So that asymptote repeats every cycle, and so does that one. Okay, so we got our period, we've got our asymptote. Let's look at the range. What does range describe again? Nico, what's range? Right, how high and how low the graph goes. Like how many values does it hit going up and down? Let's look at secant. That's the one on the left. Caleb, how high and low does secant go? Yeah, it goes infinitely up and it goes infinitely down. Lewis, since it goes up and down forever, does that mean the range is all real numbers?
No, because the asymptote doesn't go past that.
Well, the vertical asymptote doesn't have anything to do with the range, because we're looking at how far up and down the graph goes. It goes up forever and it goes down forever.
There's like there might be like an area in between two asymptotes.
So what are you saying?
Like it might go up forever from like 1, down forever from like -1. So like
Yeah, there's a gap in here, right there. The range isn't all real numbers because it never hits anything in this middle part. And it is exactly what you said. This, I get rid of those purple lines. This one is at 1, and this is at -1. It's basically, the range is everything that sine and cosine isn't. Sine and cosine is everything between -1 and 1. This is everything except between -1 and 1. So that's how we'll write it. So let's describe everything from -infinity up to -1, or what would be my other interval? Yep. Just make sure you say low, high.
Oh,
So
okay.
1 to infinity. Yep. And the domain. Let's look at the picture again. It does go left and right forever, but can I plug in any value I want for x? Yep.
I'm not sure how to write it, but like all real numbers except for the vertical asymptotes.
And that's basically how we're going to write it, yeah. We're just going to say that you can plug in any number you want except numbers that look like the asymptotes. Yep. So we'll just say all reals except the vertical asymptotes. If you wanted to be more specific, you could say all reals that are not of this form. And then you could write this down again. So anything that's not a vertical asymptote. All right, now, I'm not going to write everything down for cosecant. I just want to know what would not change out of the domain, range, period, and asymptotes. Yeah? Period wouldn't change. That would be exactly the same. Yeah?
The range would be the same.
Range would be the same. Look at these two graphs. Period's the same, range is the same, domain is the same. It's everything except the vertical asymptotes. But what would change? Right, the vertical asymptotes would be different. Instead of writing this number and that number, you would write this number and and that number. That would be the only difference. Replace this with a 0 and this with a pi, and now you have all the answers on the right. I think 5 will be a good one to stop with, and then we'll only have the graphing calculator one that's actually really easy. We'll do that tomorrow. Okay, it says find the period and show 2 cycles. Okay, what's the formula for the period of cosecant? You only have 2 choices. It's either pi over b or 2 pi over b. What is it? Yep. And what's b in this case? 3. Okay, so find the period. That's done. Find the asymptotes. Cosecant. What are the first 2 asymptotes that you hit for cosecant? Think to the table.
0 and pi.
0 and pi. Now, follow what it says on slide 6. Set each of them equal to the argument and solve. What's the argument here?
Just x.
3x.
Oh, 3x.
Right. The whole, whatever is basically after the trig function right there, that's the argument. 3x. And you said the first one was 0, and the next one was what? Pi. Now solve each one of them. That 3 is going to cause everything to shrink by a factor of 3. Well, if you take 0 and you shrink it 3 times as much, what number would you get?
0.
You stay 0. Yeah, 0 doesn't change. But this one does. If you had pi and you shrink it 3 times as much, what number would you have? Pi over 3. So now we've got x equals 0, x equals pi over 3. If that's all you write, you've given me 2 asymptotes. You need to tell me that they repeat. So what do we put on the end to indicate that they repeat? Well, we put plus the period times n, but the period's not. Right, this is the period. So, period times n. Period times n. And technically, no, you don't need this 0 here, because if you add 0 to something, adding 0 doesn't change it. So if you just wrote this, 2 pi over 3n, and pi over 3 plus 2 pi over 3n, that would be correct. If you put the plus 0, it's also correct. It's just not needed. And we'll finish the other thing tomorrow, which is pretty short. All right, let me put up the homework, but I'm going to have to change a couple problems.